is going to be given by Junfeng Fan from Leuven University in Belgium. And the topic is faster pairing hardware accelerators. So we will start in a few seconds. Yeah. Okay, please.
Okay, so this talk is basically like the second part of the previous talk, but this one we focus on implementation of pairing defined over prime curves. So the previous talk is not really a hardware talk; it's a pseudo hardware talk. I was doing math all the time. So this one it will be more hardware. Okay. So that's the agenda. So for hardware implementations, you can choose different platforms. You can use ASIC, which means you build your circuit using gates, gate by gate. For example, this is the layout of a circuit where you have all the pins around it, and you have all the cells in middle. Okay. Or you can use predefined fabricated circuit. As explained in the previous talk, you have different logic cells, and you also have modern FPGAs also give you some other building blocks. For example, you have dedicated multipliers, 18 by 18 bits, 18 by 25, and so on. You have memories, you have interconnection, and you have clock generators, and so on. Okay, so you try to make use of this resource and make your implementation as fast as possible. So the question is, how do we build a fast hardware? So I noticed that most of the audience are not doing hardware design. So I decided to explain the basic concepts using one of the isomorphism of hardware design. And you will see it, okay? So hardware is the infrastructure, right? So let's look at the evolving of a road. So in the beginning, once we had a road, something like this. You can drive on it, but you cannot really drive much fast. Right? And then we want to have a high throughput road. So what we do, we build a better road. So now you can clock your car at a much higher frequency. Right? So that's basically how we evolved. We go faster and faster. But the problem is that at some moment you have to stop. Right? You drive at 120 kilometers, it's probably okay. But 200 kilometers. It's already a bit dangerous, and it's also a bit antisocial, right? So you also get a ticket for it. If you look at the history of Intel processors, they have the same history, right? So in the beginning, you have not so fast CPU, and then you want higher performance. What you do, you improve the frequency, go faster and faster. At some moment, they stopped, right? You don't go for 5 gigahertz CPU or 10 gigahertz CPU anymore, right? Because there's somehow a limit there, right? There was a prediction if Intel processor keeps increasing the frequency as it did in the first 10 years, by the year 2012, the power density in the Intel processor will be as high as a nuclear generator. Yeah. So literally, the metal wires in a circuit will melt. So what we do if we want higher performance? So we go parallelism, right? So we put more cores on a circuit. Yeah, so that's basically, it's not invented by circuit designers. It's there, right? You want better performance, you put more data paths there, and you parallelize them, right? Of course, you cannot keep doing this, right? Because building more roads it's very expensive, and it also uses land. So in hardware, when you build something, you try to reuse it. You don't build it for one operation, you use it for many operations. And the same thing happens on the roads. For example, in Taiwan, they use it as a runway for jet fighters. In some part of China, people use the runways, the highways to transfer the animals, goats or cows. Right? That's the same idea in hardware design. Another problem that we have is the occupancy of the roads is not really balanced. It's not balanced, in directions. Also, it's also not balanced in terms of time, right? If you look at the traffic between Leuven and Brussels, in the morning everybody drives from Leuven to Brussels because they live in Leuven. Leuven is much nicer to live, but they work in Brussels. So that's what you see on the highway. And in the evening, everybody drives back, and then from Brussels to Leuven, it's very painful to drive there, right? So we have the same problem in hardware design. Yeah? At some moment, you cannot really do all the operations at this in a balanced way because you have some dependency or whatsoever. So your piece of your hardware will be idle. It doesn't do anything. It doesn't do anything. But the other part, you have a traffic jam there. So what we do, we have a very nice solution for this, right? We call it dynamic reconfiguration. So you change the functionality of your data path depending on the workload. For some reason, this idea is not implemented on highways. So, but I think it actually can be implemented, right? So the current infrastructure we have, it's not really reconfigurable. But this should be it should be fairly easy, right? So you put some traffic sign or light there, depending on the traffic. And so you go this way or go that way. All right. Comments?
The Kennedy Expressway, for example, does this in Chicago.
Okay, excellent.
And in California.
Through California. Okay, so we should do the same thing in Belgium, I think, or also in China. Anyway, so that's the basic idea, right? So you try to reuse your hardware depending on the workload. And of course, that does not solve all the problem fundamentally, right? So what we do is you try to reduce the complexity, try to reduce the number of cars on the street. So what you can do, you can encourage carpooling. For example, you can have like 15 people drive one car. Or you can encourage people to ride a bike or a bus instead of drive their big SUVs. Or if you go a bit extreme, you say we reduce the number of people, drivers. So, for example, you can impose one-child policy or a zero-child policy, but that somehow, to some people, is probably too extreme. Yeah. So, but for hardware design, if you have limited resource and you want to compute faster, so what you do, you try to optimize your algorithm. You try to make it reduce the computation, right? So it's exactly the same idea. And also scheduling is critical, right? So if you look at this cross, there are actually quite some free spaces, but because it's badly scheduled, so everybody is trying to make use of this center piece of place, and then in the end, they created a lot of dependency, right? You actually depend a lot on every car around you before any movement. So everybody has to wait, right? So if you think about this in a multi-core processor, right? It can be that this part is a shared memory, and all the roads they are independent cores. At some moment, they all try to allocate the same resource. And that creates this situation. So basically, the idea is that you have to schedule your computation such that you try to avoid this thing. Try to make the dependency between different operations as less as possible. So for hardware designers, this is what we normally use to illustrate the optimization of a design, right? We have area and we have latency, as discussed in the previous talk, right? The software implementations, they only have one number, so they cannot make such beautiful graph. So basically, parallelization means that you move your design here from this spot to this spot, right? You try to reduce the delay at the cost of larger area, right? So you somehow, if you're doing this, you have a curve like this. Complexity reduction means that you reduce the number of computation, and so you can actually move your curve towards the corner. And so that's of course very nice because you have less area and lower latency. So we talk a lot about complexity, but I think complexity is a bit vague in the context of hardware design. Because normally we use the notion of how many bit operations, right? But actually, some algorithms, they have lower complexity, but if you implement it as it is in hardware, it will be either larger or it will be either slower. If you look at the area latence product, it can be actually not as good as some algorithms that have higher complexity. Okay. So how do we optimize our implementation? Yeah, so I think it's very important that you do algorithm and architecture co-optimization. So you start from the algorithm you have, you analyze and you optimize your algorithm, and you map it to hardware, to some certain architecture. And then you analyze the architecture, right? You see, can we reuse some of this data path? Can we reduce some pipeline bubbles? Can we optimize the memory structure? Can we run it at a higher frequency? And then after this, you might say, okay, so if I change my algorithm a little bit, I can solve some problem, right? And then you go back. So hardware design is not really like a top-down design flow. It's really a loop. You do a couple of loops, and then you end up in a better design. So yeah, that's the pairing computation. Can you read it? Okay, that's on purpose. So so the idea is just to show that, you know, pairing computation can be here it's more like to be more specific, it's optimal pairing defined over Bien curves. So you have Miller's loop, final exponentiation, and you have all this operation in the extended field. And well, the most important one is operation in the finite in the baseline field. Okay, so this talk is basically about how do we do fast multiplication in FP. So this is a classic problem, right? How to do modular multiplication. For example, NIST suggested to use, or I don't know if it's NIST, but their curves that they recommended, they have this kind of form, right? So the Mersenne numbers, because reduction modular DSP will be much faster than modular random prime number. We can use Montgomery reduction, we can use Barrett reduction. There's also a very nice algorithm called Chong-Hassan. Basically, if the modular P is defined using a low-weight polynomial, and if it's monic, the reduction modular P can be done in a quite efficient way. So the algorithm that we propose can be considered as a parallel algorithm to this Chong-Hassan algorithm. So let's look at this Montgomery multiplication. It has been explained by Francesco on the first day. Basically, you have three big operations here. They're A, B, they are long integers. For example, 256 bits in this case. You have this multiplication, you have another multiplication here, and you have the third multiplication there. Okay. So if you look at the complexity, it's something like this. Oh, this is not quite true because, for example, here, because it's mu multiplied by some number modular r, so you don't have to actually compute the full multiplication. Right? If you rewrite Montgomery multiplication in different way, you will see, you know, most likely the complexity is 2n squared plus n digit multiplications. Sorry, I have forgot to mention this. N is number of digits. W is the bit length of each digit. So n times W is roughly the number of bits of the prime. Okay. For long integer multiplications, we know that there's a classic problem that's called carrier propagation, right? So if you use school book multiplication, you have to do the carrier propagation from the LSB to the MSB, which somehow creates some dependency for your implementation. Because if you want to parallelize this implementation, you have to find a way to deal with this carry. So we're looking at Barrett-Neric curves, a curve defined like this, and finite field Fp, where P is defined using a polynomial. The polynomial is the following. Yeah. So we notice that P cannot be, you cannot choose a Z such that P is a Schoedomer-Ravin number. But however, P of Z has small coefficients. So compared to the value of Z that you would choose, the coefficient is very small. And also the inverse of P of Z, modulo Z to the power 5, it also has small coefficient, and it also has integer coefficient. So the idea is that how about we do all this computation in the polynomial form instead of integer form, right? We write A and B as a polynomial, and we do Montgomery multiplication in a polynomial ring. But the saving here is that multiply here, mu of Z multiply the inverse of P of Z is much faster than this operation because the inverse has very small coefficient. It's the same idea here. For this operation, it's also much faster because P of Z is a low weight polynomial. Okay, so that's the basic idea. But there's one problem, right? So if you take an example, you have two polynomials, and we choose Z to be randomly selected Z as this. If you compute Montgomery multiplication using the algorithm, and you see that indeed you can reduce it, but the coefficient of course grows, right? Every time when you do the computation, the coefficient grows. So what we do is we need to reduce the coefficient such that the coefficient of the result is smaller than Z. So that means we need to perform division by Z. But we know that nobody likes division in hardware or software because division is too slow. But luckily, we could choose a Z as a, in such form, 2 to the power something plus a small number or minus a small number, as far as this P of Z and R of Z are prime. It's sufficient to have a secure pairing over Bn curves. So we selected, we want to achieve 128-bit security, so we selected Z as this. Okay, so and now if you look at the complexity, so here we have n square, roughly n square digit multiplications, and we have 2m minus 1 coefficient reduction, which is basically division by Z. Why is 2m minus 1? Because after the multiplication, the polynomial T of Z has so many terms. And this multiplications, you can also write down the complexity, but it becomes quite messy. So I decided to drop it and just put the word easy there. So, okay. So we made an implementation of this algorithm. We selected 64-bit Z, so to achieve 128-bit security. So that's basically how the polynomial multiplication is done. So for every multiplication, 64 by 64-bit multiplication, we do it 4 times on a 64 times 16-bit multiplier. And then there's this reduction. This mod T is basically the division by T modulo. And then we have a bunch of accumulator, and then doing some other reduction, polynomial reduction in the end. Okay. So the good thing is that the computation has no longer has carry propagation problem. So first of all, it's not long integer multiplication anymore. It's polynomial multiplication. So in the reduction part, coefficient reduction part, there's certain dependency from, so you still have to do the carry propagation from LSB to MSB, but you can easily avoid that. And then we then improved this design to achieve higher higher speed, so we used a larger multiplier. So it's no longer 64 times 16, but 65 times 65. And we use larger accumulator, and the polynomial reduction is now already done in one block. So yeah, but it looks similar. So the idea is still that you can now parallelize the implementations. So the advantage of this method is that it has somehow reduced the complexity and it's easy to parallelize. Well, the disadvantages are that it only works for specific polynomial forms. So to be more specific, the polynomial has 1 as the constant term. It does not make use of lazy reduction because the multiplication part is still quadratic complexity. Right? So then we look at R and S. So a residue number system basically is defined use a set of pairwise coprimes. So a B with set of with a bunch of coprime small integers. Okay, we define MB to be the product of all the small integers. So for any integer x that is smaller than this MB can be uniquely represented using the remainders of x modulo every small modulo, right? So for example, if we have a long integer like this, we could represent x on this base with a bunch of much smaller integers. Okay. So what's good about R and S? The computation of two numbers represented using R and S is completely distributed. Yeah. For example, you want to do x multiplied by y. Basically, you just do the multiplication in the corresponding channel. We call it channel. So every channel is basically implementing the multiplication of one prime in a base. Okay. So there's no dependency between different channels. So it's very easy to parallelize. Okay. So, but of course, every time when you do the multiplication in the channel, you have to do this modular BI operation. So it's some sort of reduction, but you can choose BI as a pseudo-Mersenne number, so the reduction becomes quite easy in hardware. So now if you look at the complexity, right, so classic Montgomery, we have 2n squared plus n digit multiplications. For the hybrid one, we have n squared multiplication plus polynomial reduction, which is somehow easy, and plus some 2n minus 1 coefficient reduction. For R and S multiplication, we only have n instead of n squared small multiplications. So the complexity really dropped a lot. And we have n coefficient reduction anyway, yeah, more or less. But unfortunately, for pairing computation or ECC, we want the modulus to be a prime. But R and S, so it's always modular MB, right? So MB is not a prime number, so we cannot use it directly. So one of the idea from Kawamura is to combine R and S with Montgomery multiplication. So the idea is that you use this MB as this 2 to the power something R here, and you do the Montgomery multiplication. But the thing is that this operation, this dividing by R, cannot be performed in this base B directly because the inverse of MB does not exist. So what you do is you really do this operation in another base. So the overhead is that you now have two base extensions basically. So you first have some number, you have to represent it in another base, and then you do the operation, and then you have to convert it back. Okay, so that's the complexity, the overhead. So base extension basically is like what I said. You try to represent the same number in a different base. One way to do it is you first recover the integer x using Chinese remainder theory, and then you compute its representation in another base. Right. So if we write this, the base extension operation in a matrix multiplication form, you see it's basically a vector multiplied by matrix of constants, because these are constants. Okay, and if you look at the operation here, so all these operations are multiplication in RNS form. So it's not quadratic, the complexity. It's really only linear. Yeah. So the hard part is the base extension. The complexity of the base extension, as you can see here, it's really n squared. Right. So we were thinking, okay, maybe we can try to use some tricks here just to reduce this part, because this is the hard part. So the constant here, bi modulo Cj, is defined as the following. It's all the small primes in base B, but bi, that's the product of these numbers modulo Cj. Okay. So you can write it in a different way. Okay. So well, of course this is valid because it's mod Cj. So you minus Cj, it doesn't change anything. So the idea is that if we choose this bk and Cj very close, they are very close to each other, then it might be that this number is very small. It's much smaller than the size of W. W is the bit length of the base. Okay. So for example, if we choose two bases B and C like this, so each base has n small primes, and each prime has around 33 bits. And then you see that the constant is actually not really 33 bits, it's at most 24 bits. So this might seem to be trivial and doesn't really save much, right? But actually on Xilinx FPGA, they have a multiplier 18 times 25 bits. So now we can really put this multiplication this multiplication, for example, this one multiplied by this one, using one multiplier instead of two. Okay. And then we made the implementation use a different set of parameters. We choose n to be 4, so every base has 4 primes, and we have w equals to 67. Okay, so you see that the constant is now really very small. So how do we make use of this? So we made a multiplier which has maybe you cannot really see it. So we have 4 18 times 69 bits multiplier. It looks very strange, but it does make sense on Xilinx FPGA because you can construct this multiplier easily. Okay. And the thing is that this multiplier can work in two modes. It first works as a 69 times 69 bits multiplier, and you use this to do all this linear part, A times B in base modulo Bi or modulo Cj, or you can use it as a multiplier for the matrix multiplication, where because this Bi, this constant is now very small, so you can actually perform 4 multiplications simultaneously in one cycle. So now this really reduced the number of the multipliers that you need to do the base extension. So and then we built the complete hardware. So it has like 4 rowers. So each rower is one channel. It does the computation of one channel. There is also some other modulo to compute one constant used in the modulo in a base extension, and the circuit is controlled by some sequencer. So it's actually a hardware software co-design, like Jeremy explained. So for such complex implementation, it's always hardware software co-design. Right? It's never owning a circuit and hardwired circuit. Okay, so in each rower we have this dual mode multiplier. We have some other really dedicated module to do operations for pairing. Some accumulators, and we have every row has its own memory block, because all the data is local, so you don't have this much data communication between rowers. Okay, so that's the result. So this work is basically what I just said. Is so use RNS, parallel RNS implemented on Xilinx Vertex 6. So it can run at 230 megahertz. One pairing computation, optimal pairing computation using Boolean curves. It can be finished within 0.33 milliseconds. Yeah, there was the one we did 2 years ago using this hybrid multiplication. It was much slower. So yeah, this implementation is very fast. It was also shown in the previous talk, but the size is very big. Okay, it's really much larger, yeah. Like 3 times larger than our implementation. So that's basically it. So this talk is very short, and it's not because lunch is after this.
Lovely. So thank you for the nice talk, and we have plenty of time for questions and comments. Questions, comments before lunch? Questions? I do have a question, Junfeng. Can you say some words about the others? Are you using some special technique for avoiding long chains and long critical paths?
Which one, for the hybrid multiplier or RNS?
For the RNS.
So
are you using carry savers or carry save others?
No.
No.
It's basically pipelining. So, oops. So yeah, you say that it's so it has like 3-stage pipelines. Otherwise, you cannot go to more than 200 megahertz.
Okay. Yeah. And this is made in the logic, or is DSP slices?
This is constructed using DSP slices.
And the others? Also?
That's only where we use DSP slices. The others are made with logic. Yeah, with normal slices. Okay.
Have you considered that possibility of exploiting more the DSP slice architecture that has accumulators and other operations besides the multiplier?
Wait, can you repeat? What?
Yeah, in the case of the DSP slice, we have more operations besides the multiplier, right? We have an accumulator and others. Yeah. Have you studied the possibility of exploiting more this architecture?
I think you might play with because it's DSP slices, so it does have an accumulator inside. Mm-hmm. So maybe you could use the accumulator there. Yeah. That can save you some slices, I think. Yeah. Mm-hmm. But other than that, I don't see why you should use DSP for addition or other operations.
Okay, more comments, questions? Yes, please.
Thanks, Junfeng. Great work. Actually, I just wondering if you can also give us a comparison between the previous talk on using binary fields per singular curves for implementing pairings, and also your work on using prime fields in terms of speed ups and also performance. Thank you.
Okay. Well, I don't have the latest results of Jeremy here, but I think I think my opinion is basically the same. So binary curves or ternary curves, you can implement it in much smaller area. So it can really go low area, probably also low power. If you look at the complexity, how many operations you do, I think pairings defined over prime curves are still using a lot more operations. For the security side, I cannot give any comment. Yeah. Yeah. So I think if one day pairing goes to smart cards or RFID tags, I think industry might like binary pairing defined over super singular curves. Well, I cannot really say certainly, but I think it does give you a much lower area and probably much lower power. Yeah.
Questions, comments? Now that you have this table, Junfeng, do you think that you can reduce further that time that you have, 0.338?
Yes, certainly. If you put more DSPs and you really parallelize it, but then the delay times area will look a bit ugly, I think, because we didn't really want to push for speed. We were always thinking that we should keep the hardware always busy and don't waste too much slices.
I see. Okay. Well, let's thanks the speaker again.